Okay, hey, I'm back. I don't know if the software that I use has some weird update, whatever it is. These videos that I make cut themselves off at 33 minutes and 1 second. The past few have done that. That's too big of a coincidence to ignore, so sounds like, I don't know, maybe I'm using a free version and that's why, but whatever. That's why there's a part 2. The video cut out, so we're starting over. Um, we did D, and if you look at D and E, they're as close to identical as two things could be. Literally nothing has changed um, except for the numbers. So I don't remember if I said all this before I got cut off or not, but you know, you might want to just pretend this had said sine and this had said cosine instead. And you could mess around with that a little bit, see how it changes things. You're pretty obvious. Oh, rats. Okay, you know what? E is actually different. Not really, but because the coefficients are both 6, we're going to get a circle instead of an ellipse. Ooh, totally different, right? But what's slightly worth investigating is when it's cosine sine, our time 0, I believe, is still going to be that point there. That's just basically is the same as point 0 on the unit circle, right? And our direction of rotation is still going to be that away. So changing sine with cosine, at least, maybe it starts me up here instead. I think it does. Does it change the direction of rotation? I think it does. I think it would start us here and have us coming around this way. You know, if one of these guys had a negative coefficient, that would change the direction of rotation. That would change the starting point, potentially. But those are some things maybe you could look into. I'm still not doing E, even though it's a circle, because I don't think I care. But yeah, I think you can figure out how the circle would work. Can't you? Moving on. All right, let's do F. For F, just think about how before we were using sine squared theta plus cosine squared theta equals 1, and we use that trick to eliminate our parameter. Well, now that we're working with secant and tan, you're going to want to use the fact that tan squared plus 1 equals secant squared. But not in that order. You would just want the 1. So isolating the 1 means that secant squared minus tan squared is 1. So memorize that. You want to be doing secant squared minus tan. But now you're just going to go after these parametrics the same way we went after the ones that had sine and cosine in them. You're going to isolate the trig terms, x minus 1. You're going to square both sides. So divided by 2, you'll square the 2, you'll get 4. That's going to be secant squared. Do the same over here. You'll get y plus 4. That's getting squared. It'll get divided by 3, so squared is 9. That'll be tan squared. Now just make sure you subtract in the right order. Do you want to be doing the y's minus the x's or the x's minus the y's? Well, because we want to be doing secant minus tan, you obviously want the x's minus the y's. And then that would equal secant squared minus tan squared, so it equals 1. And there we are. We are now in rectangular form, and we should recognize that because both variables are squared, and because the denominators are different, and because there's a minus sign down here, that this is a hyperbola. And because the x squared comes first, it's going to open left, right, like that, and have asymptotes like that. If the y squareds came first, then it would open up and down and have its asymptotes like that. So you can say it's a hyperbola that opens left, right. Okay, the center, that's still just hk, so that's still just 1, negative 4. And these denominators still tell you the distance left to right to go and the distance up and down to go. So that would mean the vertices of our two hyperbolic branches are 2 units left and right of our center. So -1, -4, and 3, -4. For a hyperbola, there's no such thing as covertices. There's literally nothing up here, right, to call a covertex. So once you've got the vertices, you're good. Now I'm not going to ask you to graph this, but imagine a world where I did. What would you do? You plot your center, it's at 1, -4. You plot your vertices, they are, what did we say, 2 to the left and right. And then your B value, so to speak, is 3. So from here, you'd go up and down by 3. And where are we? We're down 4, so it would be here and here. So what you would do is, with all 4 of those points, they would define a little rectangle. And that rectangle defines your asymptotes, because you'd go from corner to corner. So you'd have an asymptote that goes like that, and then another asymptote that goes like that. And then your actual hyperbola would have these 2 points as its vertices, and you could just sketch it in so that it follows those lines nicely. Those asymptotes, I should say. So there's your sketched hyperbola. Yeah, all right. If you're able to do that, then you should be able to give the domain and range no problem. Again, assuming no restrictions on t. You can see that your domain is going to run from -infinity up to this vertex, so -1. And then it's going to have a little break, and then it's going to start up again from this vertex, which is 3. And run to infinity. So you can pull the domain from the graph. The range, you can see, stretches forever from -infinity up to infinity, unbroken, so that's all reals. Again, things could change if we modified the t values, but I'm going to leave it to you to figure out how things would change. Again, you would just build a table of values. I'm saying t, but I guess I mean theta. But you go theta xy. Just evaluate a handful of points. Figure out where the graph starts for whatever the first value of your interval is. Figure out where it ends, and you could trace out the direction, the pattern from there. So that's F. And then there's G, which looks the same. I'm not doing G. Am I doing G? What the hell? So E is cosine, sine. D is cosine sine. Now this had different coefficients, so it was an ellipse. This had the same coefficient, so it's a circle. But how's G different from anything? It's got a minus here, so what? It doesn't do anything. If there was a negative coefficient on one of the trig functions, I'd say that would do something. So why don't we do this? Let's take one more opportunity to just use our calculator. Zoop. So obviously, we can just graph this thing, and you'll see that it's pretty much the same. So it's 5 cosine theta minus 6. So it's 5 minus 6. The other line is 4 plus 3. You can see how little I actually have to change. Obviously, it's going to come out the same. Plus 3, just hit graph, but give the full interval. 0 to 2 pi is plenty. So we're starting in the same place even, rotating in the same direction even. So nothing changed but the dimensions of the ellipse. There's just nothing interesting to talk about for G, so I won't talk about it. H. So H has something interesting going on. H is tan and secant again. This is just a typo where it says tan squared of nothing. That should be tan squared of theta, of course. But now the deal is, since tan squared is already squared, I'm going to get an x minus 1 all over 2. And I don't have to square that because the tangent is already squared. Now for the secant, that's not squared, so I do have to square that. So I'll get y plus 5 all squared. Over, it would have been over 3, but we squared it, so it's 9. That'll be our secant squared. Also, we want to subtract in the right order. We have to be doing secant minus tan. So the y plus 5 squared term is going to come first. We'll subtract from that the x minus 1 all over 2. And that'll equal secant squared minus tan, so that'll equal 1. So there you go. You're in rectangular form, but don't put a box around it yet, because it's not in the right standard form. Because what is this? Well, I see only one variable squared. So this is another parabola. And parabolas want to be solved for the squared term. So let's clear the rest out. So we'll get a y plus 5 squared over 9. And we'll add all this to the other side. Then we have to multiply through by 9. So what is this going to be? I guess it'll be a y plus 5 squared. Now this will just be 1/2 x minus 1. Now that'll be plus 1. But to get rid of this 9, I'll multiply through by 9. So this will turn to 9/2. This will turn to 9. Is that okay? No, that's not okay. We have to break down these parentheses and simplify. So, okay, fine, I'll do it. Y plus 5 all squared. Distribute the 9/2. Add 9 to it in the form of 18/2, and that will just change the sign. We'll have 9/2 x plus 9/2, at which point we'll factor out the 9/2. To just get x plus 1. So what are we? We're a parabola. It's y squared with a positive, so it opens to the right again. Okay, whatever. So finally, the important thing to talk about here is how this may be a parabola, and it may open to the right, and it may have its vertex at -1, -5. But you're not going to see the whole parabola if you graph this, because this parabola, even if we let t be any real number, we're still going to find that our x coordinates are restricted by the fact that we're defined parametrically by this tangent function. If you think about that tangent function, let me turn this calculator off. That tangent function, plain old tan, wants to go like this. That's tan. So tan squared, all these negative values, when you square them, would become positive values, and the whole graph would become a little bit steeper. So that's now tan squared, forget this. Then times 2, that would just make the whole thing a little bit steeper. Okay, not a major change. Then plus 1, that would shift the whole thing up by 1. So suddenly this is y equals 1. So we can see the set of all outputs of this x equation is actually only from 1 to infinity. So that means everything to the left of 1 on this little graph would be deleted. So we would get a point here at 1, get a point here at 1, and would lose everything to the left of that. And we've seen this before. We went over this in class. You're seeing it again. Our graph will not be the full parabola. Our graph will only be this piece and this piece. Okay? So when you go to give the domain now, you need to make sure you inherit the restrictions on the x values from the parametrically defined function, which means we only go from 1 to infinity. And then our range, you can see our range is going to be in 2 parts. It's going to be whatever the hell this is to whatever the hell that is. And how could you find that? Well, think about your secant function. Secant is the reciprocal of cosine, which means it's here at 1 asymptote. Then there's another branch down here at negative 1. And then another. So what happens here? If we multiply by 3, then this becomes 3 and negative 3. And then if we take away 5, then everything shifts down. So this would go to negative 8, and this would actually be negative 2. And in that way we can see that our range is negative infinity up to the negative 8 union negative 2 to infinity. So we can take those values now and ascribe them down here. We know that this will be negative 8. This will be negative 2. So that would be our range. So if I gave you these parametric equations and said find the domain and range, I don't need to restrict t. The x and y values get restricted by the function that they're defined by. Tan squared times 2 plus 1, it just doesn't have all real numbers as an output. It only has 1 to infinity as its output, which means our graph necessarily will lose all the stuff on the left of that. So we get that natural restriction of our domain, which leads to the natural restrictions on our range as well. That's probably the most complicated thing going on in this whole unit. Hopefully you understood it. And that's the end. That's the end. That's the last one. So it wouldn't be a bad idea to just look at it on our calculator. Make sure that you guys can hang. So if you were handed this, you'd clear. Go to y equals clear. Type in the functions 2 times tan squared plus 1. Okay, how do you square a tangent? In this calculator, you'd have to go insert, square that. I'd be a little bit scared about what's getting squared here. If it's just squaring the t or the tan, my heart says it would square the whole tangent, but I'm just going to throw another set of parentheses around it just in case. I would enter it like so. So that to me is 2 times a tangent that's getting squared plus 1. I feel good about that. Now the 3 secant, well, secant's the reciprocal of cosine, so you're doing 3 divided by the cosine of t. I'm closing up a bunch of parentheses on that too, because the minus 5 needs to be on the outside. And I feel good about that. So now I want to see the full set. This is fine. Hey graph. Did I turn it off? I turned it off. Turn it on. Turn it on. Uh-oh. What's happening? Oh, you dingus. Alright, my bad. 3 divided by dingus. 3 divided by cosine t. Try it again. So we see that top part getting graphed. Then we see the graph. It comes back up from the other side. And it kind of comes around again. And it's graphing these 2 branches twice each. I'd love to go a little lower. So we get that top branch. Then it comes back from infinity to graph it again. Then it goes back out, comes back. But what you definitely don't see is that piece over here, okay? So given that you guys have your calculator the whole time, just, use it. Hopefully understand why you're seeing what you're seeing though. You're not seeing the other piece of the parabola because this function has a restricted range, a restricted set of outputs. So our x's naturally get restricted too. All right, hopefully you get that. Anyhow, I hope this video helped you. If it did help you, then for the love of God, tell me that. Say something to me every once in a while. All right, whatever, I gotta go. Good night, goodbye.